Good morning students. Welcome to the Natural Products class. This is Chandravati. You are learning about terpenoids. In this class, I would like to discuss about zingeberene. In this class, I would like to discuss about zingeberene occurrence, zingeberene uses, and zingeberene structural elucidation and synthesis of zingeberene. Zingeberene. Zingeberene is a monocyclic sesquiterpenoid. Zingeberene is a monocyclic sesquiterpenoid. Occurrence and uses of zingeberene. Zingeberene is present in ginger that gives it a distinct flavor. So due to the presence of zingeberene, the ginger have a specific odor. It is used in cosmetics and fragrances. It have antiviral, anti-ulcer and anti-fertility effects. It is optically active and it is exists in LEVO form in nature. It is an optically active compound and exists in LEVO form in nature. Structural elucidation of zingeberene. To understand easily the structure, first I start from the structure of zingeberene. This is the structure of zingeberene. Zingeberene is a hydrocarbon because it have only carbon and hydrogens. So it is a hydrocarbon only. It have one ring in the structure. So it is a monocyclic compound and it have 3 double bonds in the structure. So it is an unsaturated compound with 3 double bonds. Structure of zingeberene is identified by chemical methods because at that time the spectral analysis is not developed completely. So the structure of zingeberene is confirmed by chemical methods and chemical analysis. To identify the structure of a molecule, first you must have the molecular formula of the compound. So the molecular formula of zingeberene is C15H24 from qualitative and quantitative analysis. The molecular formula of zingeberene is C15H24. That means it contains 15 carbon atoms. It indicates the presence of 3 isoprene units. 3 isoprene units. So it is a sesquiterpenoid. It is a sesquiterpenoid. It forms hexahydrogingeberene on reduction with platinum black. It indicates that zingeberene contains 3 double bonds. Zingeberene on reduction with platinum black, it forms hexahydrogingeberene. That means zingeberene reacts with 3 molecules of hydrogen. It indicates the presence of 3 double bonds. The molecular formula of hexahydrogingeberene is C15H30. C15H30. This molecular formula belongs to the general formula CnH2n of monocyclic compounds. So, zingeberene is a monocyclic compound. From the molecular formula of hexahydrogingeberene, the zingeberene is a monocyclic compound. The formation of hexahydrogingeberene indicates the presence of 3 double bonds in zingeberene. But these are not in conjugation. That means the 3 double bonds are not in conjugation, because if these 3 compounds are in conjugation, it may contains aromatic nature, but the zingeberene is not an aromatic compound. So the 3 double bonds in the zingeberene is not in conjugation. On reduction with sodium in liquid ammonia forms dichlorogingeberene. Gingeberene on reduction with sodium in liquid ammonia forms dihydrogingeberene. It indicates that two double bonds are in conjugation because the reduction with sodium in liquid ammonia is a characteristic reaction of conjugated double bonds, conjugated dienes. So, the formation of dihydrogingeberene with liquid ammonia and sodium indicates that three of the double bonds are in conjugation in gingeberene. Further, it forms adduct with malic anhydride. So, gingeberene, when treated with malic anhydride, it forms an addition product. It indicates the presence of two conjugated double bonds. It forms cadolene on dehydrogenation with sulfur. So, gingeberene is an hydrocarbon, completely hydrocarbon, and which on treatment with sulfur undergo dehydrogenation to form cadolene. This cadolene is a known compound at that time. Cadolene is a 1,6 dimethyl isopropyl naphthalene. Cadolene is a 1,6 dimethyl 4 isopropyl naphthalene. That means the basic skeleton structure in cadolene is naphthalene. Gingeberene is a monocyclic compound and naphthalene is a bicyclic compound. From the formation of naphthalene, gingeberene contains a 6-membered ring. To identify the skeleton structure of gingeberene, gingeberene is treated with ozone. When gingeberene is treated with ozone, it forms three products. The first product is acetone, and the second product is succinic acid, and the third product is ketocarboxylic acid. On ozonolysis, gingeberene forms acetone, succinic acid, and ketocarboxylic acid. These three products are also formed from ozonolysis of bisabellene. So, bisabellene also forms acetone, succinic acid, and ketocarboxylic acid on ozonolysis. The structure of bisabellene is also known for that time. So, this is the structure of bisabellene: alpha bisabellene, beta bisabellene, and gamma bisabellene. So, gingeberene and bisabellene forms same products on ozonolysis. It indicates the presence of basic skeleton structure in gingeberene. The basic skeleton structure of gingeberene is as same in that of bisabellene. So, this is the skeleton structure of gingeberene. And the double bond present at this place because it forms acetone on ozonolysis. It is possible only when that one of the double bond is present at here only. So, right now we have the basic skeleton structure of gingeberene and the position of one double bond in gingeberene. So, the next target is to identify the position of conjugated double bonds. To identify these double bonds, a series of reaction can be carried out. The series is as follows: gingeberene first treated with sodium in liquid ammonia in ethanol. It forms a dihydrogingeberene C15H26. So, by the addition of 1 mole of hydrogen, zingeberene can be converted into dihydrogingeberene. This dihydrogingeberene on treatment with KMnO4, it forms keto dicarboxylic acid. On oxidation with KMnO4, it forms a keto dicarboxylic acid by the loss of 3 carbon atoms. This keto dicarboxylic acid on bromoform reaction, that means reaction with sodium hydroxide and bromine molecule, it forms a tricarboxylic acid by the loss of 1 carbon atom. The formation of tricarboxylic acid indicates that the keto dicarboxylic acid is an methyl ketone. So, keto dicarboxylic acid undergo bromoform reaction. This indicates the presence of methyl ketone in keto dicarboxylic acid. This series of reactions and products are formed only when the zingeberene have this structure. So, if the zingeberene contains this structure, then only these products are formed. So, when zingeberene is treated with sodium in liquid ammonia and ethanol, it forms a dihydrogingeberene. By the addition of one hydrogen molecule, it forms a dihydrogingeberene, and which on oxidation with KMnO4, it can be converted into keto dicarboxylic acid. By the oxidation of these two double bonds, it can be converted into keto dicarboxylic acid. This ketone is a methyl ketone. So, which is on bromoform reaction forms a tricarboxylic acid. So, if the zingeberene contains this structure, then only these three products are formed. So, this is the structure of zingeberene. The structure of any compound must be confirmed by its synthesis. So, let us know about the synthesis of zingeberene. Synthesis of zingeberene is carried out from paramethoxyphenyl magnesium bromide and 2-methyl 2-pentyl methyl ketone. Synthesis of zingeberene is carried out from paramethoxyphenyl magnesium bromide and 2-methyl 2-pentyl methyl ketone. This is an Grignard reaction. So, this is an Grignard reagent and this is an carbonyl compound. So, the reaction between these two is an Grignard reaction. So, the paramethoxyphenyl carbanion formed from Grignard reagent is a nucleophile and attacks on the carbonyl carbon and forms a bond with the carbonyl carbon. As a result, the carbonyl oxygen can be converted into hydroxy group, which on dehydration forms a new double bond. By the loss of water molecule, it forms a new double bond, which on reduction with sodium in ethyl alcohol forms a dihydroderivative. Sodium in liquid ammonia means Birch reduction. Birch reduction is an characteristic reaction of aromatic compounds. In this reaction, the aromatic compound undergo 1,4 addition with hydrogen. So as a result, the aromatic ring undergo 1,4 addition with hydrogen atoms. Which on treatment with acid, the double bond is migrated to this position because conjugated dienes are more stable than unconjugated dienes. So the double bond at unconjugated position is migrated to conjugated position. At the same time, the methoxy group also hydrolyzed to form hydroxy group. The hydroxy group further tautomerizes to ketonic group. Here, two changes are occur in this reaction. The first change is the double bond at unconjugated position is migrated to conjugated position, and the methoxy group is hydrolyzed to form hydroxy group, and this hydroxy group on tautomerization convert into the form of ketone group. So almost the synthesis of zingeberene is done. There is a difference is one methyl group. If we substitute one methyl group at this carbonyl carbon, basic skeleton structure is carried out. So it is treated with methyl magnesium bromide Grignard reagent. Then the methyl carbanion is attacks on carbonyl carbon and forms a bond with this carbon atom. As a result, the carbonyl oxygen converted into hydroxy group. So which on dehydration with oxalic acid forms zingeberene. Which on dehydration with dehydrating agent oxalic acid forms zingeberene. So this is the synthesis of zingeberene. The synthesis of zingeberene contains following steps. The first one is Grignard reaction, and the second one is dehydration, third one is Birch reduction, fourth one is rearrangement and tautomerization, fifth one is again Grignard reaction, and last one is dehydration with oxalic acid. So this is about zingeberene occurrence, uses, constitution and synthesis.